We now start a new chapter in this course where we are addressing the issue of battery health estimation. And we've seen already that a battery management system has to estimate certain quantities inside the cells of the battery pack that indicate in some way the state of those cells and the parameter values corresponding to the models of those cells. And in Chapter 3, we looked at ways to estimate the battery cell state, which are the quickly changing quantities. And now we turn our attention toward estimating the parameters of the model, which are the slowly changing and the quantities that we would almost hope never really change with time, but they do in fact change because of aging effects and degradation. So we're looking at those quantities that are going to indicate or reflect some change in performance that the pack is going to be able to deliver. And these are called state of health of the battery pack. And I draw your attention again to this graphic, which is our way of evaluating progress through this course. And remember that this graphic shows us what a battery management system needs to do from the controls perspective, the algorithm perspective as it operates. First, we turn the key on to start up the system, whether it's a real key as in a vehicle application or if it's kind of a metaphorical key and maybe some other application like grid storage or something. But we turn the application on, we initialize somehow by maybe reading from memory what the state of the system was last time I turned it off and evaluating how long it has been since I turned it off, and as we mentioned, maybe running a simple Kalman filter step to update our state estimate from the point in time when I turned the battery pack off until this point in time. In any case, we initialize our system somehow and we enter a program loop. Inside the program loop, we are continuously measuring voltage and current and temperature at different points in the battery pack. And we saw methods of doing that back in Chapter 1 of the notes. And we estimate the state of the battery cells. And I've shown state of charge as being a representative state, but now you also know that it's possible using some kinds of Kalman filter to estimate the complete state. So we could estimate the hysteresis state, the diffusion current state, or whatever other state elements might be in our battery model state vector. And now we get to this section right in the center of the loop that we've called estimate state of health. Somehow we want to know, is this a healthy battery pack or is this a sick battery pack? And while state of charge has a definition that we can relate all the way back to the electrochemistry and say, I can understand state of charge in an equivalent circuit model point of view, I can understand it in an electrochemistry point of view, and they turn out to be the same if you're consistent with your modeling, and therefore we have something that we can really objectively estimate because we know exactly what it is. State of health is not so objective. State of health is maybe a little bit subjective, where you might say that a brand new battery cell has a 100% state of health. And then that state of health is going to go down over the life of the battery cell until the point where you decide that it is no longer capable of fulfilling the mission of the battery cell, whatever that is for a vehicle. It's no longer able to provide the power necessary or the energy necessary to be in that vehicle, and at that point you decide that it is a 0% state of health, and it varies in between. There may be different things that we could look at for how to quantify that health and fundamentally we have to eventually decide on some real physical parameter to estimate, or else we just have a very poorly defined health estimate. So we're going to talk about two of those in the coming pages, two things that we want to estimate, although there could be many others that form a state of health estimate, as we'll see. And just as a preview, looking forward, after we estimate the state of health of a battery cell inside of this program loop, we also are going to look at how to balance the battery cells, how to equalize their capabilities inside the battery pack so that we ensure the performance of the pack as a whole. And then we're going to revisit our ideas on computing power limits, because the methods that we looked at in Chapter 1 are quite crude, and there are better ways of doing that. Those are the major algorithm tasks. We also estimate energy. We talked about how to do that in Chapter 1. That's not a challenging thing to do after all of these other things have been done, so we don't have a specific unit on that beyond that point. Thinking about battery pack health, we need to be able to relate that to something physical in order for us to be able to estimate it with any degree of certainty, or to be able to talk about whether our estimator is working, and to be able to find a truth value against which we could compare the estimator of the state of health quantity. And if you read through the literature, when people talk about state of health, they're almost always talking about either one or both of two different things. And one of them is the capacity of the battery cells, and the other is the series resistance of the battery cells. And there's different ways of talking about what capacity is, and we'll get into that. But we can talk about a total capacity, or a discharge capacity, or a nominal capacity, or a residual capacity. All of these are different capacities, but the one that's really changing in a fundamental sense that we want to be able to estimate is the total capacity of the battery cell. And we spend a lot of time in this chapter addressing ways to estimate the total capacity of a battery cell in a good way, in a way that's consistent with the noises and uncertainties that we know are going to be present in our measurement system. The other is the series resistance, and you know from our model that there are a number of resistances present. So we have a voltage source, we might have a hysteresis element, we have maybe some resistor-capacitor networks in our model, and then a series resistance R0. When we talk about the series resistance, most people are usually talking about that resistance right there, which is the instantaneous resistance. At the moment I apply a step in current, the voltage change that we observe is due to that I times R0. But sometimes people might also be thinking about more of a steady state resistance, which would include those values as well in the computation. Either one of those could be considered as an indicator of aging, although these resistances here are also going to modify some time constants of the cell, whereas R0 does not. So you could identify one, or you could try to identify all of those in your state of health estimator. It depends on what your requirements turn out to be. Let's think a little bit about the impact of a change in capacity and a change in resistance of a battery cell. So first, the capacity. This is Q in our model. Q shows up in our model in zk plus 1 equals zk minus eta k I k delta t over Q. This is the total capacity. It also shows up in the hysteresis equation in the rate factor. I can't think of anywhere else right now where it shows up. So those are where we see the capacity in the model. And the biggest impact is going to be in the state of charge Coulomb counting equation. So total capacity of a cell is not a function of temperature. It's not a function of the rate at which I'm using a cell. And we'll talk more about that when we define some other kinds of capacity measures that people use, which are functions of rate and temperature and so forth. But the total capacity is not. It's looking at the crystal structure of the electrode materials. It's how many places are available to hold lithium. And as a battery cell ages, the total capacity decreases. So in an ideal battery cell, total capacity is constant, but in a real battery cell it is not constant, and it's primarily due to some side reactions and structural deterioration. So the side reactions are consuming lithium as we charge and or discharge a battery cell. So lithium is supposed to move from one electrode to the other. So maybe when I'm charging, it's supposed to go from the positive electrode to the negative electrode. That's the idea, but there's some that's lost to a side reaction. And that ends up causing the voltage operating windows in the electrodes to change. And if I have a fixed Vmax and a fixed Vmin for this cell, that's going to mean that I've lost capacity between those Vmax and Vmin, it turns out. The other reason we lose total capacity is there's structural deterioration. The electrode material might fragment and break off and no longer be connected, or it may chemically deconstruct. There may be some other kind of reaction where the material of the electrode dissolves, and it's like I think I've mentioned that these crystal structures that make up the electrodes are like hotels, and the hotel room holds lithium. Well, the building is deteriorating and the hotel rooms are falling apart, and there's no longer the ability to hold anything anymore. So those are the two primary reasons why capacity would degrade. You can see this if you go back to the capacity equation that we looked at in the previous course. Capacity is equal to the surface area of the current collector times the width of the electrode times the volume fraction of the solid. So far that is the volume of the active material in the electrode in meters cubed, and then I multiply by CS max, which is moles per meter cubed. So that gives me the total number of moles of lithium that I might be able to jam into the electrode. And then I multiply by theta 100% minus theta 0%, which is the operating window on the electrode. I don't use all the way from 0 to CS max. I only use a fraction, a portion of that. So that now is telling me the moles that I would normally use. And then I multiply by F over 3600 to convert moles into ampere hours. I lose capacity over time if epsilon S changes. A doesn't change, L doesn't change. But we could have structural deterioration, and structural deterioration is going to change the epsilon S. If I have a side reaction, that turns out to change this operating window here, so that I still end up with Vmax and Vmin between the cell Vmax at 100% state of charge and cell Vmin at 0% state of charge, with lithium capacity being lost, and this side reaction mechanism that shifts the operating window. CS max doesn't change. That's a physical property. Faraday's constant doesn't change. 3600 doesn't change, and so forth. So those are the only two things that can change that cause total capacity to go down. So this phenomena of capacity decreasing over time is referred to as capacity fade. And why do we care? Remember that energy is computed based on capacity. So a cell energy is equal to the cell capacity times the integral between Z min and ZT of OCV, dummy variable, d dummy variable. So if capacity changes, the energy is going to change. The open circuit voltage function of a cell does change a little bit as the cell ages, but it's mostly in this equation, the capacity, that is changing. So as the capacity goes down, the ability to store energy goes down. Capacity is also important in the Coulomb counting equation. So we identified that up here. That's where it really shows up in our models. So if we are using Coulomb counting alone to do SOC estimation, then a change in capacity really needs to be identified, or else that Coulomb count is not going to be accurate. If I am using something like, well, a voltage-based method to estimate SOC, then this capacity really doesn't show up. And if I'm doing some kind of a Kalman filter, it turns out that the Kalman filters are quite insensitive. They're not sensitive to a bad capacity estimate because the voltage correction feedback in a Kalman filter is usually sufficient to correct for a bad capacity estimate. And if we look at power estimation, the capacity does not have a significant role. It has a very minor role there. So why do I care about capacity? It's mostly having to do with the energy calculations. I may be able to get away with just using the nominal capacity in my state of charge estimator, although I will do better if I have an up-to-date estimate of capacity in my SOC estimator. And I may be able to get away with a Q nom here, but I will do somewhat better if I have an up-to-date estimate there too. But the major place is in energy. Equivalent series resistance. As a battery cell ages, its resistance also increases. Again, there's different physical causes for this, and we're going to look at some of those in the upcoming sections. But the side reactions that we talked about for capacity loss also change resistance because the side reactions build resistive components in the cell that make it harder for lithium to move. So there's extra resistance. And the structural deterioration says there's less surface area out of which lithium can enter and leave the electrode active materials, so there's going to be a greater resistance and perhaps even a lower diffusivity some people have reported, which leads to a greater resistance also. So why do I care about resistance? Why do we need up-to-date knowledge? Well, it's a major factor in the power calculation. We saw a simple way to do power calculation in Chapter 1, and I may not remember this exactly, but it's something like discharge power is going to be V min times OCV minus V min over R discharge, which is not exactly the same thing as R0, but it's close, it's related to that. So if our discharge goes up, then the ability to discharge power goes down. So it's a significant impact there. Knowing the resistance would be an important contributing factor if I'm doing SOC estimation using some voltage-based methods like the Tino method. Remember that we had an IR correction in that method. Otherwise, it's not such a major factor. With the Kalman filter methods, if you don't know resistance especially well, you can adjust the sigma V for the measurement noise to just be a little bit larger, so it looks like you've got more measurement error, and that can help to kind of detune the Kalman filter and still allow you to get good SOC estimates, even if you don't have a very good estimate of R0. It does not have a significant role in energy estimation. Really, there's no role at all in estimating the total energy of a battery pack. It's the power estimate where we really need to know resistance. So since resistance and power are so tightly coupled, the rise of resistance in a cell is commonly called power fade. So we have capacity fade and power fade, and those are two key terms when we are talking about state of health. That's what people tend to focus on. There are many other parameters in a cell model, and if you think about the cell model, we have a voltage-controlled source, we have a hysteresis element, we've got these resistor-capacitor pairs, a series resistance. So we've looked at this resistance primarily for the ESR, and we've looked at total capacity, which finds its way in the SOC equation. But there's the open circuit voltage relationship itself, there's hysteresis relationship, there's the time constants of the RC filters, different things that we might think would change over time as the cell ages. And the OCV relationship, in fact, does change as the electrodes lose capacity. For the cell chemistries that are commonly used, I think it's quite unlikely that this change would be readily detectable or measurable, although we are looking at some of that with our research right now, and it may be possible to at least get some indication of changes in OCV as the battery pack operates. Other cell parameters almost certainly change. There's no reason to suspect they would remain constant. The hysteresis rates may change, the hysteresis magnitudes may change, the resistor-capacitor time constants almost certainly do change. At this point, I'm not aware, though, of any battery management system that tries to estimate the quantities. Maybe it's just because this field has not been around for very long, so we haven't a lot of experience with old battery packs and working with them to see what makes their operation different from new battery packs and why it might be important to estimate all the parameters. But I haven't seen that yet. The dominant impact that people know about and they worry about are the resistance and the capacity. We're going to look at different ways of estimating resistance and capacity in this chapter. Some of the ways are based on Kalman filters, like we looked at last chapter for SOC estimation, and we could use these Kalman filter-based methods to estimate the other cell parameters if the application demands it. We'll see that that's possible, although that is not our objective in this chapter, really, to look at that. What are we going to do? We're going to first explore this idea of aging a little bit more, because while this particular course is not so focused on electrochemical models, I think we don't have to be quantitative. We can be qualitative and at least explore some ideas of why a cell ages. I think that's actually quite valuable. And then we'll look at a simple method to estimate the series resistance that actually works quite well. And then we'll look at some Kalman filter-based methods to estimate any cell parameters of interest. And finally, we'll spend actually quite a bit of time looking at ways to estimating the total capacity of a battery cell.